Yes, it started now.
Yeah, just another half a minute. It's that internet is a little slow, suppose. Yeah.
Yeah. So.
Okay.
Okay, we
Please.
can start now. Right.
We are ready.
Yeah. Good morning, good afternoon, or good evening, everyone. I'm delighted to welcome all of you to this special lecture series, which is being conducted in celebration of the International Year of Quantum Science and Technology, a worldwide acknowledgement of one of the most revolutionary scientific movements in history. 100 years have passed since the pioneering findings that gave rise to quantum mechanics, a theory that has not only transformed physics, but also completely reformed how we see the natural world. The Indian Association of Physics Teachers is organizing nationwide webinars on quantum mechanics. This seventh webinar is an effort of IYQST RC23, Himachal Pradesh, and focuses on the theme Teaching Quantum Mechanics and Physics Education Research Studies, including new paradigms and emerging trends in quantum technology. So thank you for joining us today in this exciting journey. It's a pleasure to extend a warm welcome to our distinguished guests and participants. At the outset, I would like to warmly welcome the National President of IIPT, Professor P.K. Ahluwalia, whose continued leadership and vision have been a source of inspiration for the physics education community across the country. I would also like to extend a special welcome to the Secretary of IIPT, Mrs. Rekha Ghorpade, whose untiring commitment and organizational leadership have played a vital role in enabling events such as this one. And most importantly, a very warm welcome to our distinguished speakers for today, Professor Chandralekha Singh and Professor Geshe Pospish. We are truly honored to have you with us. Professor Chandralekha Singh, a renowned physicist and educator, is the founding director of Discipline-Based Science Education Research Center at the University of Pittsburgh. We eagerly look forward to the valuable insights and perspectives she will share with us today. I would also like to warmly welcome Dr. K.K. Mashood from HBCSC Mumbai, who is chairing today's session. Dr. Mashood is a renowned figure in the field of physics education research in India, known for his insightful work on conceptual understanding in physics and student learning. We are grateful for his presence in today's sessions. I welcome President RC23, Dr. Kuldeep Sharma, and all the dignitaries present here today. Finally, I would like to express my heartfelt welcome to all the participants from across the country who have joined us today. On behalf of IIPT, once again, I welcome you all. And before we start, I would like to invite Professor Ahluwalia, President of IIPT, to say a few words.
Thank you very much, Sapna. And I'm really delighted to welcome Professor Chandralekha Singh for this very special webinar on teaching of quantum mechanics and PER actually. And I would like to tell the participants here that Professor Chandralekha Singh has done a lot of work on teaching of quantum mechanics. I think that's a seminal work which she has done, which has been noticed a lot in the world around. And we also have been inspired by her work in India. So thank you, Professor Chandralekha, for being part of this series. And we are looking forward to your insights into what or the way we would see quantum mechanics evolve in teaching as far as quantum revolution 2.0 is there. So I also welcome Dr. Mashood, who is chairing this session, and Ma'am Rekha, who is with us all the time. That is why we are able to conduct this. Professor P.C. Deshmukh, and my other colleagues in IIPT who are here in this meeting. But a large number of people are there on the YouTube also, ma'am. So I think this will have a very big reach, this lecture. Thank you very much.
Thank you, sir. So let's begin, and I would now hand over the stage to Mashood.
Oh, sorry.
No problem. I'll make it short. Thank you, Sapna. Thank you, Dr. Sapna. Thank you, Professor Ahluwalia. As usual, it's an honor to host Professor Singh and a privilege to listen to her. whenever like we approach her to support PR initiatives in India, she's always kind and always encouraging, like to do whatever possible on her part in that regard. And I think this is the second time that we are few months ago, we had the fortune to listen to another talk of Chandralekha. So since the time is a bit short, I will not spend more time, because I think now almost everyone knows she needs no introduction in Indian PR community or otherwise. So over to you, Professor Singh.
Thank you so much. I'm so delighted to be here. And, I hope we have some great discussions here. So I wanted to start out by saying that I'm very grateful to all the students and postdocs who have worked with me. And I wanted to start out by saying that, I basically recognized early on that we really need to think about how to improve student learning of quantum physics. So this is an article I wrote in Physics Today almost 2 decades ago, where we actually created a taxonomy of student difficulties in learning quantum physics. And I'll just give you an example, for example, that, if you think about time evolution of a quantum state. So we gave to students from 9 different universities, undergraduate and graduate students, questions like this, if the wave function initially is a linear superposition of the ground state and first excited state, will the probability density depend upon time? And what we found is that, this was a very difficult question. These were students from US universities, and only 43% of the students provided correct response. And it turns out that the probability density in this particular case will depend upon time, because if you look at the quantum state, since it's a linear superposition, the ground state will evolve as e to the power minus I EHT over h bar, and this one as e to the power minus I E2t over h bar. And so since the phase factors are not the same, if you take the absolute square to calculate the probability density, there will be these cross terms that will not go away. But the common incorrect response was that the time dependence is not there in the probability density because there is an overall constant phase factor. So you can see that students are overgeneralizing what they are learning about stationary state wave functions or energy eigenstates, and wave functions that are linear superpositions like the one that is given over here. So with this example, what I want to say is that what we found is that regardless of the background of the instructor, teaching style, textbooks, or students, the difficulties across different universities were very common. And it was often due to the subtle issue of distinguishing between related concepts and overgeneralization of concepts. Like, for example, overgeneralizing stationary state concepts to non-stationary state concepts, to non-stationary state. And you can see that part of the issue is, if we are going to teach quantum mechanics as a course in differential equation where we keep doing, now do infinite square well, and I'll show you how to solve a differential equation, and then finite square well, then harmonic oscillator, then some other finite, some other hydrogen atom or this or that. If the entire course becomes, a course in solving time-independent Schrodinger equation, is it a surprise that students are having difficulty realizing that the most fundamental equation of quantum mechanics is time-dependent Schrodinger equation? That's the one for which Schrodinger got his Nobel Prize, not time-independent Schrodinger equation. It's true that if the Hamiltonian doesn't depend upon time, then you can actually do separation of variables and you can get time-independent Schrodinger equation, and you can find a complete set of stationary state, which can be used to find this linear superposition like the kind that I showed you here. But the point is that students will struggle with time evolution of this kind of a state if they are only remembering h psi is equal to E psi, which is definitely not the most fundamental equation of quantum mechanics. But the fact that students have this universal difficulty in learning quantum physics helped inspire us to actually develop research-based learning tools. And of course, development of research-based learning tools is an iterative process. We think carefully about the learning objectives, for example, for time evolution of quantum state. We think about the initial knowledge of students. What do students already know that we can build on? What are they having difficulty with? Because if you know their knowledge structure at the beginning, after traditional lecture-based instruction, you can then think about learning tools that can actually help students build a more coherent knowledge structure where there is less room for those kinds of difficulties. And of course, we want to develop learning tools that are guided, inquiry-based learning sequences. By guided approach, inquiry-based approach, I mean students have to do the thinking, because we cannot do the thinking for the students. All the research in physics education shows that students have to be actively engaged in the learning process. So you have to make them do the thinking at all points, as opposed to teaching by telling approach. And we do cognitive task analysis both from our own perspective, what do we want students to be able to do, and what is the order in which we want them to be able to think about. But we also want to be able to actually interview students and think about it from their perspective, because it's really important to catch all the blind spots, because if you don't actually understand where the students are coming from, you're going to miss out on a lot of things. So we did all of these things, and we have been developing these things called quantum interactive learning tutorials, or QUILs. And these, as I said, use student difficulties as resources, and they use a guided approach to learning, and they provide hints and feedback as needed, and they bridge the gap between the quantitative and conceptual aspects of quantum physics. And they use computer-based visualization tools that we have adapted from many sources, like open source physics simulations by Bologna and Christian, QVIS simulation, PhET simulation. We adapt things from all over. And these things keep students actively engaged. That's what I was telling you. Inquiry-based is really important. Each of these QUILs comes with a pretest that you can give after traditional instruction, and a post-test that you can give them after students engage with these QUILs. Notice that, the QUILs are best given in class when students are working in small groups of 2 or 3, but you can also give them as homework if you wish. Now, many of these have warm-up exercises that students can also do. And of course, these things are based on cyclic process of development. So let me just give you an example of this time evolution quilt, because I just showed you the difficulty that students are having. And in this particular quilt, in the pretest, students are actually going to be asked about a stationary state and a non-stationary state, like the one that is shown here, and what is the probability density and whether it depends upon time or not, and explain their reasoning. What you see is that, as I already told you, only 43% of the students provide correct response. So at this point, in the quilt, the first thing you tell students is to actually look at a computer simulation. So here I'm showing you time-lapse pictures, and you can see that the vertical axis is psi star psi, the probability density, and the horizontal is the position. And you can see this is at some time t equal to 0, future time, future time, future time. And what you see is that the probability density actually is depending on time. So at this point, the student has a cognitive conflict. They are in a state of disequilibrium. Why is it that I thought the probability density shouldn't depend upon time? Because the time dependence of this stage should just have been overall phase factor, but that doesn't turn out to be the case here. So this is a really great time to help students think about why Hamiltonian is what governs the time evolution of the quantum system through the time-dependent Schrodinger equation IH bar del psi over del t is equal to h psi. And that's why the eigenstates of the Hamiltonian, the energy eigenstates or the stationary states, play a key role in the time evolution. And if you don't have a stationary state like this, then the time evolution of a quantum state is going to be non-trivial, and this probability density will depend upon time, even if the Hamiltonian does not depend upon time, right? And notice that it's really important to help students think about these different representations of knowledge. For example, this is the visual representation, to help students develop a robust understanding of these concepts. So you can see that I'm showing you here different quills that we have developed. And by the way, they are all available on Fizzport if you're interested. And if you can't find the Fizzport site, please let me know. These are how the students did after traditional lecture-based instruction. And this is how the post-test is how they did after they engaged with the quills. So you can see students are doing a lot better. And also notice that there are many quills like Mach-Zehnder interferometer, Stern-Gerlach experiment, quantum key distribution. These are all things that are actually connecting with the second quantum revolution topic. All of them use two-state systems. So these are systems that are very simple. You can even actually do these things with students who are not necessarily physics majors, like they could be computer science major, engineering major, and all of those people have become interested in the second quantum revolution. I will say more about this quantum key distribution quilt later on, but let me actually say how we are going through a really exciting time, right? Because last century was the century of the first quantum revolution. And this thing not only actually helped us formulate the quantum formalism, but gave us transistors, semiconductor devices, lasers, and nuclear energy. And now this century, this entire century is going to be really exciting because we are going through the second quantum revolution. We have just begun the second quantum revolution in the last few decades, and it is brought about by the exquisite control that we have over quantum systems like atoms, molecules, individual electrons, and the way that we are able to manipulate them to actually actively explore and create, new states of, to manipulate quantum states of matter and use quantum superposition and entanglement to do quantum computing, quantum communication, quantum simulation, and quantum sensing. And even though you may say right now we are at a very, very, very preliminary stage in quantum computing, communication, or quantum sensing, by quantum sensing, I don't mean like, MRI machines. Those are the first generation of quantum sensors. But I'm talking about the next generation of quantum sensors in which we are going to be able to harness quantum entanglement to do even more precise sensing. So we are basically at the beginning, and we really need to prepare students and get them excited about being part of this exciting second quantum revolution. And in fact, talking to people in industries, I can tell that there are lots and lots of jobs available. In fact, they are already saying that in the last few years, thousands of jobs have actually not really gotten filled. So for example, you don't even have to be in a quantum proficient job where you are literally actually, for example, manipulating qubits. Qubits is quantum bit using different architectures, for example, as superconductor qubit or ion trap qubit or neutral atom qubit or semiconductor qubit. That's not necessarily what you need to do. You can even be somebody who's a cryogenics engineer who's cooling things, because you need to cool system down to avoid quantum decoherence. You can be a computer architect, you can be a systems engineer, you can be a business developer, nanofabrication person, mathematician doing mathematical computation, you can be a teacher, electrical engineer. So there is the material scientist, chemist, physicist. There's job for all kinds of people in this industry because this is a transdisciplinary field, and we really need to get students excited early on. And so that's why in the US, National Science Foundation on Office of Science and Technology Policy of the White House put together a team of 25 people, and we basically were tasked with coming up with key concepts in quantum information science that even high school students should be taught. And you can go to this website and you can see what we came up with. And these are the key concepts. And now we have a lot more explanation for what we want students to be able to do in these things, even at the high school level. So you can see, we want students to be able to learn quantum states, that quantum states are different from classical states. Quantum bit and qubit, again, the same, this is related because qubit can be only 0 and 1 bits can only be 0 and 1, whereas quantum bit, on which quantum computer will run, or you will do quantum communication or quantum sensing, could be a linear superposition. But when you observe the qubit, you can only measure it to be 0 or 1. So that's the important thing about quantum measurement. That quantum measurement is weird. It actually collapses the state. So we need to make sure that students actually understand that. And also the fact that quantum measurement will be different depending upon what is the measurement basis that you choose. That is different from what happens in a classical computer using classical bit. It's not that the basis matters there. Also, quantum entanglement, as we said, gives us a lot of advantage in all of these kinds of applications, whether you're thinking about in quantum computing, communication, or sensing. But of course, decoherence is a huge issue. So that is something that is going to make this whole century extremely exciting. And that is going to be the biggest impediment in whether we are ever going to, for example, be able to make a quantum computer that can break Shor's algorithm and give us quantum advantage. Nobody knows whether that will ever be achieved. But anyway, whatever we are going to be able to do, we are in this Sputnik moment of quantum computing and quantum communication, quantum sensing, and all the progress that we are going to make will be very, very exciting, regardless of whether we are able to actually get to the ultimate goals or not. So of course, all these applications are very, very exciting. So I already said that decoherence is going to be making all of these things really difficult. And that is why, the reason in the mid-90s this field got a huge impetus is not only that Shor came up with the Shor's algorithm that talks about how you can factor products of prime number in polynomial time as opposed to exponential time, which is really important for encryption and safety over internet. When you're actually doing your credit card transactions over the internet, that is what makes it safe. The fact that, RSA protocol, it depends upon, your credit card number being multiplied, for example, with products of large prime numbers, and factoring them out takes exponential time in the string of that thing. But if quantum computers were there, they could actually break it in polynomial time, almost n cubed. So the fact that he showed that, he actually made National Security Agency in the US and every other country very interested, even in India, for example. And so every country is very interested because they're all afraid. In the US, actually, they're saying by 2035, in 10 years, they're going to actually try to make the credit, all the security, the encryption stuff, not use RSA, but use some other protocol, which is post-quantum encryption scheme, right? But, Shor did one other thing that he is less well known for, which is quantum error correction. He actually showed that, even though quantum state is fragile and the state decoheres very easily, you can actually correct error. This is something that people didn't really think was possible, because in the 80s, Feynman had actually said that we should be thinking about using quantum physics to do computation, but nobody paid attention to it because of the fact that we were not really sure that we could do quantum error correction. So Shor not only actually came up with a scheme for how you could actually break the credit card transaction and other encryption, for which is really important for countries' national security, but he also showed that you could correct error. So we were getting better and better at, and also at the same time, we were getting better and better at doing manipulation of individual quantum system. So it was mid-90s that suddenly we went into the second quantum revolution phase. This is the beginning of the second quantum revolution phase. And now if you think about quantum computing, there are three interrelated things. Yes, quantum computers are going to give us massive speed up on certain type of problems, and they depend upon this quantum bit, which can be in a superposition of 0 and 1, not just 0 and 1, even though when you measure it, it'll be either 0 or 1. But it all depends upon coming up with quantum materials that are actually going to be able to withstand decoherence, because the computation time should be larger than the decoherence line. And since the quantum bits, these things are so fragile and the system decoheres so easily, we have so many different architectures right now. You have heard of superconducting qubits that IBM and Google have, and many other companies have, ion traps, neutral atoms, semiconducting qubit, photonic qubit, all sorts of things. But nothing is like, you can't say that this one is necessarily a front runner. You cannot say, I mean, even though neutral atoms are doing really well, or superconducting qubits are doing really well, they all have their own problems with materials. And so you can't really say, oh, I know for sure that this is going to win. And at the heart of it, as I said, is this time-dependent Schrodinger equation. That is what is governing the entire CPU, central processing unit, of a quantum computer. And right now, we just have toy models, which are more like wind-up toys. But the point is, as I said, the ultimate goal is that maybe we are actually going to be able to make scalable quantum computers that would actually be able to factor. For example, here is a number that I gave you, and these are its factors. It takes exponential time to factor this number into these two numbers. And so this is something that quantum computer will be able to do in polynomial time, right? So the point is that these kinds of advantage has made, and since those things are related to national security, not just your credit card transactions, which it is, that's why all of the national security agencies are interested. Also, you have heard of Grover's algorithm. Grover is, I think he's in Bombay now. He basically came up with this algorithm, which actually gives quadratic advantage in searching unsorted data lists, right? And so this is also, even though it's quadratic advantage, it's very good because, instead of 1 million searches, you'll do 1,000 search. So it will give you a lot of advantage if we could have a quantum computer. So what we are doing in developing the tutorials that we have, is thinking about quantum interactive learning tutorial that will help students learn the basics of quantum computing. By the way, I also wanted to say that you may not be interested in Shor's algorithm and Grover's algorithm, but the point is we are more interested in thinking about those things that have maybe societal implications, like making better fertilizers, better drugs, like thinking about solving climate issues and stuff. So those kinds of things, different kinds of quantum simulations that we are going to be able to do are extremely exciting. So making a scalable quantum computer would definitely be a very good thing. So what are we doing in these tutorials? So we start very basic. The first thing that we want students to be able to learn is what is the difference between a classical bit, 0, which can only take 0 and 1, 2 values, and a quantum bit, which can be in a superposition. And notice that, we often take example of, say, polarization states of light. For example, you can have horizontally polarized light, vertical polarized light, but you can also have a superposition of where the only constraint on this state of this light, the photon polarization state, a single photon's polarization state, is that alpha squared plus beta squared be 1, but it's neither vertical nor horizontal. In fact, when you do the measurement of polarization of light, you don't even have to measure it to be vertical or horizontal. You can choose a basis which consists of plus 45-degree polarized light and minus 45-degree polarized light. This is what gives quantum a huge advantage because we are talking about a two-state system, and yet we are talking about a case in which you actually don't have just one basis. It's not just like 0 or 1. It's not just like vertical and horizontal. You can look at this basis and another basis, or you can put an eye here and another eye here. That would be another basis. You can have infinitely many bases even in a two-dimensional Hilbert space. And this is the beauty of quantum mechanics. And the fact that quantum measurement, what our quilt is helping students learn, is that when you measure something, if, for example, if this was your quantum state and you measure it in the horizontal vertical basis, even though this is neither horizontal nor vertical, you have now a 50% probability of collapsing your state into horizontal and 50% in vertical. But you have no way of knowing ahead of time what a single photon, which is in the state, will do. So this is the beauty that we are going to actually take advantage of, that we are going to harness to be able to build quantum communication networks, to be able quantum networks, quantum internet, quantum computer, quantum all sorts of quantum simulations. For example, as I said, like in building and making drugs, making fertilizers, solving climate issues, on many other issues that are really important to us. Now here, I'm going to show you that in the quilt, we basically use the normal notation, because notice the beauty also of the second quantum revolution is that people are saying, let's get away from the exact qubit architecture. Is it superconducting qubit? Is it semiconducting qubit? Is it neutral atom? Is it ion trap? Is it photonic? Let's not worry about it. Let's just go to this new notation of qubit 0 and 1. Because this is like, all of the physics of which qubit, which kind of architecture you're using, what material you're using, is all buried in this thing. So this is a language that will be more palatable even to engineers, even to computer scientists. So in this language, if you have several qubits, let's say that you had n qubits, then for n qubit, you have 2 to the power n possibility, because it's possible that all of those things can be in 0 state, or maybe one of them can be in 1 state and the rest is 0, or maybe this one can be 1 and all 0. So you can see that there are 2 to the power n possibilities. And the beauty of quantum physics is that this is going to, your quantum state can evolve in a superposition. So this is the thing that is giving the quantum advantage in a quantum computer. So students are learning that if you just have 300 qubits, basically there are 2 to the power 300. The quantum state is a superposition of 2 to the power 300 things. Many of these states are entangled states. And the great thing is you don't need any register, you don't need any, physical memory to keep track of it. 300, say, electron spins can automatically keep track when you are evolving your system of these 2 to the power 300 things that are more than the number of known particles in the universe. So this is the beauty of quantum computing. So students are learning in this quilt the difference between how a classical and a quantum computer work. So what they're learning is that in a classical computer, you are still going to actually, let's say that you have n, bits, you still will be initializing all the bits. Let's say that you initialize them all to 0. When you gate your system, that means when you're doing time evolution in your central processing unit, CPU, you are basically going to change that from one of those states to another one and another one and another one. So it's only going from one state to the other one. And then finally you read the answer depending upon your computation that you're doing, based upon whatever your computation is, you finally read out your answer. On the other hand, in a quantum computer, yeah, you initialize your state again, into some, maybe you set everything to 0, whatever you wanted. But then the great thing is that this time-dependent Schrodinger equation, the most fundamental equation of quantum mechanics, is again evolving your system via the Hamiltonian of the system in the superposition state, in this entangled state. And if you can think of good algorithms, if you can think of clever algorithms like that Shor's algorithm that can factor products of prime number in a polynomial time, or Grover's algorithm for giving quadratic advantage on searching unsorted data, or any of those things that are naturally of interest to physicists, like solving this Schrodinger equation that we are not able to solve for tough problems. We always make a lot of approximation if we want to do things analytically, because we can't do it. Quantum computers might be able to solve many of those quantum simulation problems much better. But of course, at the end, you have to, when you know that your answer is close to the correct answer and it's peaked about some answer, you're going to read the output. And that's when quantum measurement becomes important. And you have to apply this Born rule, and you project out your answer. And this will be the probability of getting the answer. Notice that, the answer will be peaked about some answer that you think is correct answer. But in quantum mechanics, there is a probability that the answer will be wrong. But it's okay if you can check whether your answer is correct or not. And if you got, say, for example, exponential advantage, say in Shor's algorithm, then even if you got your answer to be wrong a couple of times, it's still okay, because you are going to be able to run it a few times, and then you will be able to check. So if I know I'm looking for the factor of 15, and factor of 15 are 3 times 5. This is a small number. I can do it in my head, but I was showing you that large number that will be very difficult to factor. And it takes exponential time on a classical computer. Even if you get it wrong, and by multiplying those numbers, you can easily check whether it's correct or not. You have to run it a few times, and that exponential advantage, that n cubed advantage that you get, will still be very useful, and we can run this on quantum computer. So now, as I said, DiVincenzo criteria is also something that we are trying to build a quilt out of, quantum interactive learning tutorial. And so DiVincenzo basically said that in order to build a quantum computer, we need to think about how to input and output the quantum information. We need to think about quantum memory and quantum central processing unit. But most important thing here that we cannot forget is the fact that quantum state is fragile and it can decohere very fast. So we need to do computation in a time that is much shorter than the decoherence time. And that is why you are seeing so many different types of qubit architectures like superconducting, neutral atom, ion trap, and semiconducting, and all sorts of things. And we don't know which one will win. We will even see, for all you know, in 20 years or 30 years, a combination of all of these. But we really need to get students excited about this wonderful field that is so, there's nothing out there right now that is so exciting, that is really at the forefront of trying to make a difference in something that doesn't exist. So I'm also showing you a quantum interactive learning tutorial that we have developed that is already available on Fizzboard, which is on quantum key distribution. This is, if you're not going to meet with somebody, if you are Alice and Bob and you're interested in sending encrypted information, and you're never going to meet the person meet the person, then there is no secure way classically to exchange that information with that person. Quantum mechanically, there is. And that is because, quantum measurement collapses the state. So if somebody is eavesdropping and they try to intercept what Alice was trying to actually send to Bob while generating a shared secret key, Eve will have to send something to Bob, but sometimes her state will collapse into something that she wouldn't know. And in that case, she will be sending to Bob something that actually will be wrong. And when Alice and Bob at the end do some kind of parity check, they would know that somebody was eavesdropping, because that quantum measurement, collapsing the state and changing the state, we are trying to make a lemon into lemonade. So in this case, we are trying to harness something that kind of, is a disadvantage in terms of decoherence, because, quantum state cannot be cloned also. But here we are taking advantage of it in actually generating a secure key, because Eve's presence will be known, because there'll be at least 25% error that is generated. So we wrote a paper in 2020 in Physical Review Physics Education Research on an interactive tutorial on quantum key distribution that my student and I developed. And you can see that students work through these things, and they actually use non-orthogonal polarization states of light to do this. Right now, a student and basically students have to actually think very carefully about why there will be at least 25% probability of error being generated if Eve was eavesdropping here. So if you're interested in checking out the quilt and use it with your own students, please do, because you can see that in the pretest, students didn't do as well after traditional instruction. And after engaging with the quilt, students are doing significantly better, and they have a much, much more robust understanding of how to actually generate a secure shared key with somebody if you were never going to meet with that person, and why presence of Eve would definitely be detected. I'm also developing right now a hands-on kinesthetic tool. Basically, like it's this, like block cube. I don't know if you can see. These are basically cubes, which are basically hands-on tools for helping students learn quantum physics. And you can use this with students at any level, even high school students, first-year students, nth year students, anybody can use it. It's basically, what is a block cube? Block cube is basically, it's like a dice. It is basically a simplification of the block sphere that you must have heard of, right? Block sphere actually represents all the possible states of a qubit, of one single qubit, a two-dimensional Hilbert space. Now, the simplification here is that this is only a two-dimensional thing. So notice that in this, there are only 6 possible states, plus z, minus z, plus x, minus x, plus y, minus y. So we have simplified the thing, but notice that it does a very honest job. You can think of plus z as 0, minus z as 1. Okay, so the ones that are opposite to each other, they are orthogonal states. They are basically mutually exclusive states. You don't even have to say, if you're teaching high school students, you can just call it mutually exclusive states. Okay. On the other hand, plus x is not mutually exclusive from plus z. So in fact, plus z is a superposition of plus x. Plus x is a superposition of plus z. So it helps students actually learn things by doing it, by rolling a dice, by rolling a, by flipping some coins. Students can actually learn a lot of quantum physics in a very, very rigorous and honest way. So 0 state, for example, you can represent with plus z, 1 state with minus z, and other pairs can be, for example, plus x can be this, minus x can be this. And now quantum measurement corresponds to asking different kinds of questions. So quantum measurement is like, you can ask a plus z question. You can ask a z question. Z question will be, is the quantum state, plus z or minus z? And notice that the answer to this question will depend upon what is the top phase. Top phase is basically the state of the system. That is the state that the qubit is in. So this block cube is representing a qubit. And so if you are in an x state, for example, and if you ask a z question, since x is a superposition of plus z and minus z equals superposition, you have a 50% chance of getting plus z and 50% chance of getting minus z. And you can flip a coin and decide, okay, if it's head, then I'm going to assume that my state collapsed into plus z, and if it tails, then it's collapsed to minus z. But before you flip it and get that result, you don't know which one it will be. So quantum mechanics is probabilistic. Now, if your state is plus x and you ask an x question, this is the only one in which you're going to get a deterministic answer, because the answer to plus x, the x question will be plus x because your state is plus x. If you were in minus x, then your answer will be, again, deterministic in the x question because the 100% chance that you're going to be in the minus x state. Now, if you ask the y question, then you again have like, 50% chance in the x state of getting either plus y or minus y. You'll have to flip a coin and decide based upon whether it's head or tail, which one it's going to be. So, you can really play a lot of games. So, you can have students actually learn a lot about, quantum measurement by doing these kinds of activities, which are very hands-on and kinesthetic. You can teach students about time evolution of the quantum state by doing rotations of these block cubes, because time evolution is nothing but rotation. And notice that you can rotate things about different axes, right? You can rotate about z-axis, you can rotate it about x-axis, or you can rotate it about y-axis. And notice that if you are in x state, and if you're rotating about x-axis, the x state is not changing, but everything else is changing. But if you now rotate about some other axis that is not the top phase, let's say you rotate about minus y-axis in the clockwise direction, for example, your state will be different now. So now your time evolution is actually, taking you to a different state. So all of these things, actually show you that rotation about different axes is important. It's like, because if you're rotating about different axes, that's like having different types of Hamiltonians. And so all of those things you can teach without even doing a lot of mathematics, but doing hands-on activities with block cube. So one of my students, Dan Lau, right now is developing a quantum interactive learning tutorial using block cube that can be used even with first-year college students or even with high school students, because there is very little mathematics here. There's no, differential equations and stuff. At the most, you have linear superposition. So you can teach time-dependent Schrodinger equation just as rotation, using this. So that's what we basically do. And right now, basically, these are the learning objectives for how we use the, I'm not going to go over it because, right now we are seeing that, the preliminary evaluation in one-on-one interviews is useful. I also wanted to just talk about the fact that we are doing some stuff with my collaborators, Emily Edwards and Diana Franklin, as part of this National Q12 partnership for high school level. And, there are lots of benefits to starting early. Students will find it intuitive. There'll be more diversity. Students actually can think about careers in this area because they'll get excited and they won't find it spooky. So I want to summarize here and take questions. I want to make sure that I've conveyed that quantum information science, which is basically, upon us, we are in the second quantum revolution or quantum information revolution. It's a very exciting field that should be something that we should really get our students excited about. There's so many different kinds of career opportunities, and really quantum industries are saying they don't even have enough people to participate in this. So they really are desperately looking for students to participate in this and be part of it. So we, as quantum educators, have a key role to play in preparing students for the second quantum revolution. And early exposure to these key concepts in an intentional manner in using research-based tools is really important also for equity and inclusion and getting students to be excited about these things early on. Because otherwise, if students just hear about it, once they are in BSc or something or BTech, then, like at that point, the diversity is already gone. So it really needs to be done early, and partnership between academia, industry, and even national labs and all is really important to give students a holistic education and have them, like, for example, get visits from people in industry, get visit from people in national lab, because they can also talk about what they have been doing. And so these kinds of things can be extremely interesting and useful for helping students understand and get a holistic view of this, and while we actually help them with our research-based learning tools to be ready for the second quantum revolution and play a key role in it. So thank you, and I'll take any questions you have.
Thank you, Professor Singh, for a wonderful talk, very insightful, walking us through the fascinating facets and exciting times ahead as far as second quantum revolution is concerned. If you have questions, please raise your hand, or you can type in the chat box as well. So let me begin, Chandralekha. Like you have mentioned some initiatives that you are carrying out, introducing these concepts to high school students. There are some people who are saying that these are very abstract, advanced concepts, and you are introducing it to high school students. And there is ample evidence from PER which shows that they struggle even with Newtonian concepts. So what is the point? So what are your thoughts on this, and some cautionary advices or pedagogically, what should we be careful for this exercise to be more than some inducing some excitement, to be a much more meaningful learning exercise? What should be done?
So thank you. So I think that, like I was saying, one of the things that you can think about is how to not teach things in a way that actually will give students the wrong impression, right? So I think that, the block cube approach that I talked about, in which you're using these cubes to help students learn, that is basically something that will not give students the wrong impression, because we are really doing a very honest job of helping students learn about things like superposition, things like what will quantum measurement do, without really teaching any differential equation or very hardcore mathematics and stuff. You just need to actually have simple superposition. And so you can teach a lot of things. And I actually disagree with the fact that, just because Newtonian mechanics is difficult, we shouldn't be really teaching quantum because quantum is more difficult. I would say actually that being exposed to something early is actually a good thing, because then you develop an intuition. We all grew up in India, and we were learning our own mother tongue. My mother tongue is Hindi, so I was learning Hindi and English at the same time. It didn't really seem like those were really two different languages, in terms of like uh, that it was one thing was so much more difficult than the other one. I was just saying, what I mean is that or with your teacher you should be talking in this language, with your parents you should be talking in this language, or with somebody else you should be. So you kind of switch on and off your brain within a second, because you see that person and you're like, oh, I should be talking in this language. So same with quantum mechanics. If that when you're looking at the quantum domain, you should be thinking about things being in a superposition state, not just 0 or 1, but it can be in a superposition of 0 and 1. All of these things can be entangled. It is just basically the whole superposition that evolves. Students can realize, oh, I'm talking about electrons, I'm talking about atoms, I'm talking about molecules. I should be thinking about quantum as opposed to the classical thing. So students will learn much better if their brains are learning these things from an early age, to switch back and forth between those kinds of things. Because as I said, we all grew up learning different languages, and it never seemed like it was kind of like really difficult. But when you learn something, when you actually just grow up and never before that, it seems like, oh my gosh, what is this quantum physics? So I think that the spookiness will also be not there if people realize that things at the microscopic level can be in a superposition. It's not just 0 or 1, it's a superposition. It's true that when you measure it, it will be either 0 or 1, if that's the basis you use. If you use the basis of 0 and 1, then it will be 0 or 1. If you use a basis of 0 plus 1 and 0 minus 1, then it will be, even though initially before the measurement it will be 0 plus 1 or 0 minus 1, after that it will be one or the other. So I think that, teaching those children early those kinds of things, and what is the quantum advantage you are getting from this, would be very useful. So of course applications should also be at the forefront, like quantum computers. What are they able to accomplish that classical computers will not actually be? Many of the students are very excited about the societal implications of things. They are like, I want to change the world by actually fixing the climate issues, by actually fixing the food security issues, right? And right now, for example, Haber process is very like energy intensive, which is used for making fertilizers. But like quantum computers might be able to actually make it more efficient, the fertilizer issue. And so that could make, help a lot with actually nitrogen fixation problem, that is very crucial for food security. And so I think that what I'm saying is that you can focus a lot on, or drug delivery, drug design. The fact that design of drug, we are not going to do random combinations. Quantum computers will be able to find patterns, that are going to be much better. We might even be able to combine, quantum with AI, machine learning, and basically like, be able to do things much better and find much better patterns in things. So all of those things can get students excited about it. So even the societal implications of things should be at the forefront. But even teaching the physics using these kinds of kinesthetic exploration, and if you do it in small groups, and as I said, my student is actually right now developing a quantum interactive learning tutorial, which is a research-based learning tool which uses block cubes.
That makes sense. Thank you.
May I come up with a question, sir, if you allow me?
Oh,
Sure.
please.
Can you say your name?
I'm Manish Khare. Actually, I tried doing the hand raise, and but that was not allowed.
Go ahead, Manish.
Okay, thank you, sir. Ma'am, I'm Manish Khare from Pune, and I have a question basically regarding the teaching quantum mechanics to 11th or 12th class students, where most of the times, or maybe many times, teachers end up, basically the teachers whom I know, end up trying to explain quantum mechanics in a simple way by giving the analogs of classical mechanics. And at the end, they just explained that this quantum behavior is analogous to particular behavior or property of classical mechanics. And beyond a point, they end up uh, presenting it like a chamatkar type thing in Hindi. And then they end up at the end stating Finman as if you don't understand, then nobody understands because the teacher doesn't understand, like that. So what is the solution possible? It reminds me of a quotation of Einstein that anything should be made as simple as possible, but not simpler. So
Thank you. Yeah,
yes,
so I totally agree with you. I mean, like, I don't personally like this kind of thing where, like you make it seem like it's some kind of miracle, because that is, I don't think that that is helping students. In my opinion, we should be doing honest job with students. And I would say that this block Q approach, by the way, we wrote a paper in American Journal of Physics and another one in the Physics Teacher using this block cube approach, and I'm going to send it to Sapna. And Sapna, can you send it out to everybody? So I think that, in that particular approach, you can see the physics teacher article. We also have 10 videos, where we demonstrate how you can actually, help your students think about doing things with block cube. But as I said, right now, one of my students, PhD students, is working on a tutorial using block cube too. And I think we should be doing an honest job, not using mathematics, but conceptual things, but using, say, kinesthetic explorations like this to help students do things in a way where it doesn't look like a miracle. Because otherwise, students are going to get the wrong impression. We should really be teaching, rigorous and honest things, but without mathematics, without too much mathematics. And as I said, the approach that we have outlined in the physics teacher article that came out in January or February of this year is basically very, it doesn't require any mathematics. So I think that what I'm saying is that there is definitely a way to teach quantum mechanics, but making it seem like, this is some kind of miracle is not really the approach. In fact, even at the college level, related to what you were asking, I would also say that, even in upper level thing, people who start with Bohr model and then go make a transition, a lot of times people have seen that students now have difficulty understanding things like uncertainty principle, because they have difficulty seeing how the position and momentum of the particle is not well defined at the same time, because of the fact that they have that Bohr model stuck in their brain. So I think that it's really important to teach students the correct thing. And I would say, but not by correct, I don't mean mathematics. I'm saying don't use mathematics. And the block cube approach is one of those approaches.
Thank you so much.
Can I ask your question? Can I ask just one idea? Ma'am, do you think that cultural or institutional differences affect the way students engage with these learning tools?
Cultural and I would say cultural differences might impact things only to the extent that if suppose, the tests, I would say, like if the focus is too much on tests, because the way that the tests are happening, like assessments, then students might not focus on certain things, because students actually want to focus on those things where they feel like, they would actually be rewarded by grade and other things. So if suppose, like you say, oh, let's do this block cube activity, but there is nothing about those kinds of things in your assessment, then they might say, oh, no, I'm not going to pay so much attention. If you say, oh, I'm going to put some students in small groups and work with it. So I think that in that sense, what I have noticed, Sapna, is that in India and in the US, the education system is very different. Here, there is no standardized exam at all in K through 12, right? Up to 12th grade, it's your teacher who's doing everything. your teacher will decide, the physics teacher will give you the physics grade and chemistry. So there is no standardized exam. Everybody is sending whatever their own teacher gave. And that is a very different, so the teachers can teach block cube and they can test them on block cube. And so students will pay attention. So there is a lot of focus on these group activities because teachers are assigning point for those group activities that the students are doing. Because if you are completely responsible, because I know I myself have 2 kids, and one of my kids is like, oh, I don't like my teacher always like, making me do things. I'm like, no, do it, because, like, I mean, your teacher is doing it for a good reason. But the point is, like, he wasn't always excited about participating in those group activities, but I think that it was really good for him. So I'm just saying, those kinds of differences about, like, what matters, like, is this thing going to be on the test and stuff, will be really important. And I think when you said institutional thing, I think again, institutional, like NCERT, like I remember when I was growing up, that was the thing that was making the syllabi. And the point is, like, if they are making all the curriculum, and if this is not something that they will be graded on, then the students may not pay that much attention. So there needs to be some way to incorporate it in the, overall. Yes.
Thank you. We'll take one last question from Professor Ahluwalia. The next speaker is already here. So, unfortunately.
Okay. Thank you very much, Mashood. Professor Chandrlekha, it was a wonderful lecture, I must say.
Thank you so much.
And there were 2-3 things which were coming to my mind. I think you talked about the language in India, the way we really learn those languages. The real problem occurs in languages when people start teaching us grammar, actually. Then we find out what is the need of all these things that we are being taught. Can you think that we can really bring that kind of a paradigm shift, that in learning all this, you don't need to learn the whole grammar of quantum mechanics to begin with. And it's a good point to start with. But I think maybe, for example, simulations with the dices we try to do when we try to simulate radioactivity, for example. I mean, that's a very interesting problem to do with the help of dices itself. So when we bring this, do you think that we need to really completely switch off the old quantum theory till the Bohr model if we want to really make them appreciate all these things, and then bring them into the quantum theory which began with proper quantum mechanics itself? And maybe then these kinds of tutorials which you have developed, maybe those will be very, very helpful. What is your thought on this?
I actually agree with you. I mean, and moreover, I think I totally agree with you. And I feel like, by the way, I am not in favor of completely not doing Bohr model, but I think that the amount of time that should be spent on it should be such that, students don't just remember that. Because notice that, and as you develop expertise in a particular domain, I think that people have a way of refining their model, right? I mean, like when they see that the simpler models are not working in this context, then they would say, okay, let me think about how I can refine it. And because I don't think that that model is useful in this context. And then they'll go to the full, Schrodinger picture, and they're like, let me think about it this way, or, So I think that we need to think about what is the simplification that we can make. And like you were saying, do just enough, but not like, mislead students. So that's my thought on this.
Another thing which I want to say is, Professor Chandrlekha, you must be knowing that we are having International Conference of Physics Education in India this time in the month of December. And we hope you will be there, and I would extend on behalf of IAPT an invitation for you to come there. I think that
yes, ma'am. I also extend the invite to you.
Thank you so much. Thanks a lot.
So we are looking forward to host you at Chandigarh, Ropar, Mohali, everywhere. Please do come.
Well, thank you.
Grover, I hope you know, he is the member of C14 Physics Education Commission. And he is, in fact, the one who has brought ICP in India this time. And we are working very hard. IAPT is part of that effort.
Thank you so much. Thanks a lot.
So we are looking forward to host you and take you around the other major centers which are in our neighborhood, in particular the Punjab University, which is the oldest institution which commenced the physics honor school as early as 1934
Thank
at
you so
Lahore.
much. Thanks a lot. I think I'm going to now actually, thanks a lot. I really appreciate being here. And I think now I'm going to let Gesha speak, and I'm going to also be here for her talk too. Thanks a lot. I really appreciate all the.
Thank you, Chandralekha. And thank you everyone for patiently listening. As you know, we are running short of time, and next speaker, Professor Post-speech, is already here. So over to you, Sapna.
Yeah, thank you, Dr. Mashood. So now we have second talk of today. Second talk is by Professor Geshe, and I think she's there only. I've seen her name.
Yes, she is there in the.
Yes, I'm here.
Yeah, welcome, Professor Geshe.
Thank you.
Your video is off. Now it's.
Yeah. Now we can see you also. Yes.
Yes.
So Mashood, will you like to give her a brief introduction?
Sure. Thank you, Dr. Sapna, and welcome, Professor Geshe Post-speech. She is chair of physics education at TU Dresden, Germany, and is involved in many major projects relating to quantum mechanics, particularly a community-based development of the quantum concept inventory and the development of quantum concepts via two different states, different two-state approaches. So this pilot analysis analyzes different teaching approaches via two-state system, and the aim of her research is to determine which context of a two-state system is best suited for which quantum concepts with a design-based research process. I think it's a good continuation of what Professor Singh has been speaking, and looking forward to your talk, Geshe.
Okay. Thank you for your kind introduction, and I'm very happy to speak to you and to give you some of my thoughts about teaching quantum physics. And I will also shortly touch a bit upon the results you said, and on which a paper will come forward. But now I will just start this one. I will share the screen. So I hope you see now my presentation.
Yes, we can see it.
Yes. Thank you. And so I'm very eager, and it's a really important goal of mine to have both aspects of modern quantum physics in one taken together. It's the quantum concepts, so to say, the pure quantum theory we have, and the application of the quantum theory and the quantum technology, and to see this together. And I will give you some of my thoughts about this. The first is I will start with a very brief introduction on and a few words on the second quantum revolution. Then I will talk a bit on educational foundations. And then I will give you a proposal of a modern teaching approach and touch upon some empirical evidence. And then I will talk a bit about how to combine quantum theory and quantum technology. So I'm sure Chandralekha has already told about that the quantum physics has also changed the physical worldview, and that the conceptual physical questions really led to a long-lasting debate about quantum interpretation, which was in the end also the root of the modern quantum technologies, because it was really the search for clearing up these interpretations to really understand what is behind quantum physics that drove the quantum technologies, the technology needed to develop modern techniques in manipulating single photons, production of entanglement, for instance. And this was kind of, if you want to say, it was talked about experimental philosophy, because at some point, some 40 years ago, it became possible to really find new ways for isolating quantum objects, for manipulating and controlling quantum objects. There were some key results on the theoretical side, mainly Bell's inequality, which really boosted the experimental techniques, and then the experiments, among the first of them, the aspect experiment and some related experiments. And this then led to the Nobel Prize of 2022 for experiments with entangled photons, proof of the violation of Bell's inequalities, and pioneering quantum information science. Here you see the strong relation of basic fundamental research, just wanting to know what is physics about, what is quantum physics about, and really at the same time to lay the basis to open up the doors for the development of quantum information science, which so much gives us today. And I heard that Chandralekha told a bit about quantum computer and quantum cryptography. And so the second quantum revolution came quite quietly, but had a very strong and really up until now accelerating development of new technologies, new applications. And on the other hand, it became obvious that you have to think differently from classical physics, that you have to develop a quantum thinking. And with this, I do not mean that that quantum physics is somehow mystic or spooky, but it's just a different set of rules. In the discussion, you talked about Newton mechanics. Newton mechanics is some sort of rules. Quantum physics is a different sort of rules, and you have to know when to apply what and what, which, and in what conditions. And therefore, I wouldn't say that quantum physics is more complicated than Newton mechanics. It's just different. It's just different, and you will have to get used to these different kinds of thinkings. And this, you have quantum physics, of course, you have everyday devices developed for quantum physics. It's a laser and it's a transistor. And these quantum physics instruments led to applications we are now developing today: quantum sensors, quantum metrology, quantum internet, quantum information, and so on, which we don't know where will they lead in the end, but which is really an exciting development. And so we really, and this development also presents a big challenge for physics education research. And you have many researchers, many research groups trying different aspects also for the different levels we have. We have the public, the general public that wants to know what is being done in research labs. We have the school level where teaching quantum physics is important to really prepare the students to be able to participate in the societal discourse on quantum physics and its applications, and to have a basic understanding of quantum physics. Then, of course, at the university levels, you go into more depth. You really have the quantum physics for the physicists, the chemists, for engineers, computer science, and many other parts of science. And then you see it's the intersection of different disciplines you need. You need the engineers, you need enabling quantum technologies, you really need not only the physicists and chemists, but also the material scientists, the computer scientists, and so on, for really developing the science and also for developing course modules, materials, and so on we would need. And here we come to the educational considerations we have in this morning. It's learning quantum physics is an exciting journey that opens the door to understanding the fundamental nature of our universe. That's one of the aspects we have. With technology such as quantum computers, we stand at the cusp of a revolution that promises to bring the quantum world into many aspects of our lives. So it will really have an impact, such as classical computers had on our lives. I think quantum computers also. And quantum physics isn't quite magic, but it requires an entirely novel set of rules to make sense of the quantum universe. And this we have to take in mind if we think about these. And as I just spoke about the general public, the students at school and the university, you have different levels for different teaching goals. One is just to give awareness of the quantum world, to evoke enthusiasm, of interest, discussion visions, somehow give some basics of kind of a feeling on a qualitative level of the quantum world. Then go one step further, perhaps at school, be that the students are able to describe quantum concepts, to know how they work together, how you get the different aspects working. And if you are more advanced, you go to applications and use quantum concepts for understanding and explaining quantum technologies. And you have, if you think of teaching, these are the different levels you have to be aware, clear of what do you want to reach, an awareness, kind of an understanding, or really a bit of an advanced understanding and the possibility of applying quantum concepts. And so I want to stress what underlies all of these three levels. The first is really quantum physics is regular physics theory. There's nothing mystic, nothing spooky. It's just a mathematical described and experimentally validated physics theory. And we have experiments in the first quantum revolution. We have the theory. We have different a problem in learning, which is often the physics interpretation of the mathematics and the applications we have. And also in the second quantum revolution, which mostly deals with single quantum objects, we have experiments with the two-state systems, which are quite important for in this second quantum revolution. We have the theory, the non-locality, entanglement, Bell inequality, and we have also applications Chandralekha already mentioned. Then, if this is a case and quantum physics is important, quantum physics is also indispensable for general education. And there I have to say, in Germany, quantum physics was part of the high school curriculum since decades. We are teaching quantum physics in high school since the 60s of the last century. Of course, it's more I would call it classical quantum physics with the Bohr atomic model, the photoelectric effect, and so on, which has to change now, I think. But it really has a tradition to teach quantum physics in high school. And that is, of course, also promoting this possibility of general education. And then we have the quantum technologies which are relevant for general public and really also for professional development. We have the quantum technology, quantum sensing, quantum computing. We have professional career opportunities. We have a high demand for specialists who can really think quantum and work in this interdisciplinary field. And of course, we have the societal impact on the impact of quantum computers on data generation, data use, and really other new applications we don't know today with possible impact on the everyday life. And now we go, what of these is important for teaching? Where should we focus on? And there was a paper with Merzel and al. Identifying what the experts in quantum physics and quantum and physics education really agree on are important. And if you go to the homogeneity axis, what most people think important and what they most often call, you have four aspects you have here. It's a superposition, it's a Heisenberg principle or uncertainty, it's an entanglement, and it's the quantum measurement. And those four concepts really seem to be the basis for the future teaching of quantum physics. And here you have also different aspects of description, and it depends on your target group on which side you go. If you go to the formal mathematical description, or if you go to the conceptual side. Superposition relies that quantum states are described as elements of a Hilbert space, and each quantum state can be described as a linear combination of basis states. That's the mathematical part. If you want to stay on the conceptual side, you would say a superposition state is a special state with undefined properties, where the properties you have are not defined. As Chandra Lekha said, it's not 0 or 1, it's a superposition of it. And such is kind of a special state where you don't have defined what property really there is. And from this you see that superposition is a basis for all other of these three concepts. It's a measuring process. Mathematically, you can describe it as a projection on basis states. And conceptually, it's an unpredictable, as a rule, an unpredictable change of state. And you could circumscribe it as resolving the superposition to random values and the associated states. And also uncertainty relies on the superposition, that you really can describe the same state with different values. As Chandra Lekha said, you can ask the Z question, the Y question, the X question. That's the uncertainty. You have different observables, the Z, the Y, the X, represented by operators, and most of them non-commuting. And you can circumscribe it. There are no fixed values for all physical properties at the same time. If you have the property, the Z property fixed, then you don't have fixed the X property. And if you have fixed the X property, the Z property is no longer fixed. And you have the entanglement if you have several degrees of freedom, and you would describe the quantum system as a tensor product of the Hilbert spaces. And conceptually, it implies that the parts of the system cannot be separated, and you have a holistic description of quantum objects and quantum systems. So you see, you can describe the mathematical part and the conceptual part if you want to avoid the mathematics. And what is important is really to see somehow, to have explained the difference of classical and quantum physics. You have the mathematical physical basis you have here, and then you start thinking about what you are doing. You have the time evolution with a Schrödinger equation, which is a deterministic equation, and which hence gives a deterministic evolution of a quantum state. And this is, so to say, something about the quantum state itself. It's a kind of an ontological view you have. But now you ask as an experimenter, for instance, you want to know something about the quantum object, the quantum state it is in. And there you go to the epistemological view. And in order to know that, you have to measure it somehow. And we know the measurement gives random events, random results, and it's not deterministic. It's indeterministic. And there you have the contradiction. It's kind of, in classical physics, the ontological view and the epistemological view somehow are very much overlapping. They are perhaps not completely the same, but very much the same. You cannot distinguish them. In quantum physics, you have the distinction between this existence of the quantum object and what we can know about the quantum objects by a measurement. And if you are clear about this difference, then you can accept all the rules and the results we have. And you can start working with these quantum properties and to develop the quantum technologies. And now is the question how to teach these, how to approach this. And in this, I think, as the quantum technologies are very new and require a new thinking, we also have to renew our thinking in teaching and to get rid of some traditional aspects, which is perhaps in Germany, with its long tradition of teaching quantum physics, perhaps more difficult than in other countries who just start teaching quantum physics in high school. And there we think about the empirical evidence on the students' learning. If you start in the traditional way, you have the central problem of the interference of classical properties and quantum properties. You talk about things as particles or waves, and students are used to treat, for instance, electrons as particles and light as a wave, and they don't change it, and you have the classical properties of particles and waves. And therefore, things as the uncertainty is often explained with uncertainties of measurement itself, no accuracy of measurement, and so on. And there you sometimes just have ad hoc explanations if the students really don't know how to agree with this. This is one strong argument to really leave out these classical relations, to start with classical physics to explain quantum physics, but really to teach quantum physics from the scratch. And one of my PhD students has really developed a teaching approach for quantum physics for grade 9, for students who are around 15 years old. And they didn't hear in physics anything about waves, though we were not induced to teach something about waves, but we just only got the we just started with the quantum physics without recurrence to classical physics. And so we need some of, so we avoid many of these problems which we have here, the confusion of time evolution, to see probability as inaccuracy, the wave-particle dualism. We not even mentioned it in treating quantum physics in order to really have a clear quantum view on this. And in another study, we compared the teacher-student, which were at university in their third study year, who had really attended a lecture series on traditional quantum theory. And we compared them to high school students who had really a two-state approach via polarization approach learned. And we tested them their understanding of the measurement process. And when we did that, we saw that the teacher students which were really at university and had studied quantum theory really had a more classical thinking, you see here, than the students who really had a modern approach, avoiding wave-particle dualism and the interference of classical and quantum concepts, who really went more to the quantum thinking. And similar results, which really quantum thinking, we also had with those students in the 9th grade, the 15-year-old. They really could develop a conceptual quantum thinking stance, which showed that it is possible to teach quantum physics in a conceptual way, phenomenological way to 15-year-old students. And you really have to be, and that was one of the strategies we used, really to be very aware of language and models. So really may clarify for the student that we are using models and we are really working with the language. I perhaps can show it. We really emphasize the use of models. We describe the measurement result. We represent the states. We didn't say the states are vectors or the measurement results are. We really describe the measurement results with a wave model or with a particle model, you could say. And we had really language conventions. In this teaching, the students were really very made explicit for measurement and classical physics. We only speak about measurement, and the quantum physics we speak about the measurement process, and we use the word state function instead of wave function. And also the superposition, we said in the classical physics we say overlapping kind. And in the quantum physics, we speak about superposition to make clear that the superposition principle is something special of quantum physics and not classical. So we really made the students clear that there was a difference between classical physics and quantum physics. And we used mental images and anchors, multiple representations, and really simulations to teach the students. This is very important when teaching quantum physics, especially if you don't have the mathematics at your disposal, but really the physics. And the approach is the spin-first approach. You have a mathematical, relatively easy access if you have two-state systems. It's physically meaningful in numerous examples. You can use very many physics systems. You can describe at least the basic behavior by a two-state system. And there are big advantages for learning because you really have the Bloch sphere, the Bloch cube, the Bloch circle we sometimes use. And you have the polarization as a modal experiment that you can take. And you have different contexts in which you can have those two-state systems. One is the double-well approach. One is the polarization approach together with hands-on experiments and with simulations. You can choose a single photon. And in the paper we prepared, it became clear that you can really reach a very good conceptual quantum understanding by the double-well approach and the polarization approach. It's a bit more difficult with the single photon approach, and the quantum cryptography approach still has to be validated in this thing. And the polarization as a model for the spin we are using is very much appropriate to use it. You can really use the spin. You can also introduce the spin to 15-year-olds on a phenomenological logical basis, and you can really use the polarization, and you can use symbolic notation and really prepare kind of mathematical notation, which is sometimes very much appreciated by the students, because they have something concrete where they can write down the states, which gives them some possibility about speaking about the quantum states. And therefore, this Dirac notation is really of advantage, even if you don't much further than using it as a language for describing quantum states. So, and now we come, how can we combine the basic concepts of quantum physics and the quantum technology? And which technology are in which way suited for achieving this goal of the combined goal of learning about quantum physics, the basics of quantum physics, and the quantum technology. There you can have the phenomenological approach, where you, for instance, start with Schrödinger's cat, which most students already have heard, where you have the entanglement of the radioactive atom and the cat, or linguistic description, where you perhaps can also use some explanatory video clips. Or you use really a pragmatic approach. You start with a concrete experience, a question and anchor using quantum technologies. Then you make the conceptualization, and then you go back to the application of the quantum technologies. And here I want to say yes. You have it here somehow indicated. You start, for instance, with the quantum cryptography or quantum key distribution with an encrypting procedure, which needs a two-state system. You have here in yellow, you have the application, the quantum cryptography, and in the blue you have the physical description, so that you really see for the encrypting procedure you need a two-state system. The generation of the quantum key needs a superposition and the properties of the measuring process, which is also needed by the exchange of the key itself. And in order to be secure before an eavesdropper, you need the uncertainty. So yet that you really see these basic quantum concepts have some implications for the quantum application, and similar for the quantum computer, where you have the processing of the quantum information, the qubits. You have the logic gates you need, and you have the superposition and the time evolution. You have an algorithm realized by quantum gates. You need the entanglement. With a quantum computer, you really need the entanglement. And you have the result of the computation, where you have to be aware of the properties of the measuring process. And if we go back and really want to say what is now suitable for teaching at school, you can make kind of analysis. What is interesting for the students, which here I measure just by the YouTube calls of the 10 most highlighted YouTube videos. And you here have the number, which you see with the 5 is the most interesting and 1 is the least interesting. And you have a weight, so to say. The weight is 0.2 for the interest. It's how well can you elementarize the application? How complicated is it? How relevant is it for students and in public media? What is also the relevance? And how well do you see the working of the quantum concepts? Is it far away or it's not so far away? And of course, this is subjective, but if you take this line and the weight, you end up with kind of a number, and you see the quantum cryptography. Somehow the quantum cryptography and the quantum teleportation, you end up quite high. With the quantum computer, it's more difficult. It's not so easy to see the basic quantum concepts. And the quantum sensor is just not so interesting, but I think it can be made more interesting if you really see that you, for instance, can use a quantum sensor for medical purpose. This could kind of criteria for deciding which is a suitable topic from quantum technology for teaching quantum physics. Yes. And then you have kind of a proposal for a teaching sequence where you could start with the existence of single photons, where you could talk about interferometer and double slit experiments, where you introduce superposition and measurement process, uncertainty and entanglement. And now I will just shortly go through all these 5 steps, 5 phenomena we can have, and where we also have technological applications. We use kind of the coincidence method for really showing that we have single photons, the Mach-Zehnder interferometer, which is used in different variations, the properties of the measuring process, which is important, and the uncertainty relation. So the first is generation of single photons with parametric tone conversion with a nonlinear crystal, and where you really can have kind of polarized photons where you have 2 at the same time, one which serves as a signal and one is the idler where you can do experiments with somehow. That's the first thing where you really have to see where you have a single photon detector and where you really observe that you have to have both detectors, the detector A and the detector B, have to detect a photon, really to show it. But if you have here a beam splitter, only one of those may click at the same time in order to really have one photon and really to have the photon as a single object. And you see also here how it looks like on an optic table with the laser coming in, the detectors here in the black boxes, and really the laser and the 2 beams we have here. And then the Mach-Zehnder interferometer can be used to analyze the behavior of those photons, to have really 2 states. You really have a superposition of possibilities. In the double slit, you have the slit 1 and the slit 2, and in the Mach-Zehnder interferometer, which is basically the same, but more spatially extended, you have the interferometer arm 1 and the interferometer arm 2, and you can use this and to make all the different experiments. And there are simulations you can use to really explore the behavior of the photons in the Mach-Zehnder interferometer, and also to add, if you want to do it, so the mathematical description. What does a beam splitter do? It's a superposition. It makes a superposition of a photon, and the second beam splitter also goes back, and so you can really treat this Mach-Zehnder interferometer in a more qualitative way or also in a mathematical way. And then you can use the delayed choice experiment or treat the which way information and also do the quantum eraser. In this way, approaching the measurement process. What is happening if you have the measuring process? Here you have a real experiment, and here have you a modal experiment with a laser and polarization. That is really for exploring the behavior of photons in a double slit and really to see the properties of the measurement process. And here we really go, we have the state, we really have the superposition, and we have the different aspects where you reduce the superposition. The photon comes here in a superposition state and then is detected either here or there, which means kind of the projection we had before. And then what is also important is to see the decoherence as a model for the measuring process, which really is one reason is it's fundamentally important because it can clarify the position of the measuring process, and it's also important for the quantum computing, as Chandralekha said. And decoherence has in this time practical consequences for quantum computing. The next point is the uncertainty, where you can really also make a model experiment showing the student that property is not fixed once and for all in a quantum object, but really depends on the measurement. If you have one measurement, you get from the superposition state to horizontal or vertically, and if you have a different measurement, you really can have both the possibilities, the diagonal plus and the diagonal minus, and if you have the vertical, also the diagonal plus and the diagonal minus, so that you have on the screen, you have photons with a D plus property and photons with a D minus property, whereas you started here only with photons with a D plus property, which means that this property is uncertain, it's not determined once and for all, but can be changed dependent on the measurement. And the alternative for this polarization experiment would be a third experiment with cross Stern-Gerlach apparatus. You know, perhaps you know that. And the last one is the entanglement, where we really can do kind of thought experiments. Or here you have some real experiments with entangled photons, where you see that Alice and Bob both always click at the same time and not crisscrossed. And that is, there are over statistical correlations you have, which then are used in experiments on entanglement and different states, which are important from a theoretical point of view, but which are also important for the quantum computing, where you really need the entanglement. And the last one you have is the quantum teleportation as an application, where you really need the entanglement, where you see how it works, that you really have here entangled photons, and you have a photon with Alice, which where you want this information to be transported to Bob. And you may not measure this, because then you lose the information on the alpha and the beta. And what are you doing is you are entangling this already entangled photons. You are entangled with the third photon is here. And now you have the information which is coded here as an alpha on the whole system. And then you really make a special measurement. It's a Bell measurement, where you really get now the EPR pair with Alice, and you have a photon in a state you don't know which is the state. Therefore, I here have the tilde with Bob, and Bob knows he has the information alpha and beta. He's only not quite sure what it is exactly. And then here you have the reason why the teleportation of quantum information only goes with maximal light velocity. It goes not instantaneous because Alice has to give her measurement results via a classical channel to Bob, and then Bob knows exactly what he has to do with his photon in order to get the original state, the original information, which really is the application of quantum teleportation, and where you get information from one place to another place without measuring, but not faster than light, and which could be of application in quantum computers for moving information from one memory register to another memory register, and really use this quantum teleportation. Many thanks for your attention, and I'm open to your questions.
Thank you, Jesse, for a wonderful talk, blending very nicely the technical, the application, and the educational aspects of it. We are open to questions. Please raise your hands or type in, or you can unmute yourself and speak as well, whichever you prefer. Yes, Professor Ahluwalia, go ahead, please.
So thank you very much, Professor Geshe. It was great listening to your very thorough lecture linking quantum mechanics with technology. One question which was coming to my mind, on technology aspect, you showed a lot of pictures there. So these are available to the school students when you are introducing this kind of a course? That is my first question. Second is, when you are talking about this introduction of both the technology and the quantum science, at what level you are pitching these courses? Are they at the school level indeed, say at the K-12 level, or they are at different levels?
I am not sure which pictures you mean which are available. It is so that in teaching we do mostly analogy experiments with lasers and polarization, and we refer to these experiments with a video. There are videos which can be used so that the students really see the videos and can so see how it is working. And we also work with simulations and model experiments. Those are the three tools we are working with. And the level I'm teaching on myself is teacher education at university, where we also try to do it in a way that the students really can put it and can use it again for their teaching at school. We really talk about how they can focus on the concepts, how they can visualize the different concepts, and we avoid too much of mathematics. But we nevertheless we observed that a moderate measure of mathematics does help the students to clarify some of the conceptual considerations, because they really know what is possible and what is not possible. If we stay just on a qualitative description, or if we use analogies, they are not always sure how much are the analogies working and where do the analogies stop their meaning. And in this sense, as some kind of basic mathematics is helping the students to get a feeling what is working and what is not working.
There is another question which was coming in my mind, was this, that you talked about teacher students, whom you are teaching this course. What about the teachers who are already in the schools, and if they also need some kind of a training to introduce these courses in the schools? Is there some effort in that direction also?
Yes, we are doing that. That we have, for instance, that we have prepared material. The curriculum in our state has changed recently, and this we took as an opportunity to develop materials, and we also do regularly teacher professional development where the teachers are coming, where they get kind of introduction, and where they have the opportunity of working with the material, of asking questions, and then really use this material in their own teaching. Yes. We are doing this also for the in-service physics teachers.
Oh, thank you very much. And
Thank you.
once again, I would like to extend an invitation to you to come to India for ICP 2025 conference. And I'm sure that we will make it in the month of December. So today we had two very distinguished speakers, and we would love to have them in that ICP 2025 conference itself. So thank you very much for coming again. We look forward to such very stimulating lectures. And I think I would say that you have made this special web series very special by your very, very enlightening talks. Thank you very, very much, both Chandrika and Geshe. Thank you.
Thank you.
Any other question? I fully agree. Geshe is now becoming a very familiar figure in the Indian PR community.
Yes.
Earlier also we had a talk from her in PER series.
Few months ago, right? Yes.
Yes. So thank you very much. It was such a nice talk. Wonderful session.
Thank you.
So one clarificatory question I wanted to ask, you said analogy experiment. Why do you call them analogy experiments, and are these developed by your university, your group itself, or you collect it and make a portal?
Partly we developed it ourselves. I just let me see. For instance, this was developed by my assistant. The idea is older, and it's an analogy experiment because we are here not really working with single photons. We just take a laser, we have a polarizer, and here we have a double slit. You don't see the slits. And we can make a different polarizer on one slit and on the other. And here you have, again, a polarizer for the analysis. And we call it really an analogy experiment because it's not a real quantum experiment. It's not with single photons, but it really gives a very similar experimental results you could also observe with single photons. And therefore, we make it also clear to the students that it's not a real quantum experiment with single photons, but it's a model or analogy experiment, which we are doing here. And so that the students are really aware of it, because with single photons, you would need a detector, a single photon detector, which we cannot expect to be available at school, but this can be available at school. This or very similar experiments can be made also at school.
Also, in your talk, you were using terms from philosophy of science like epistemology, ontology,
Yes.
etc. In your teacher training, do you invoke them? If yes, to what extent?
Yes, in the teacher training, I do this, and I try really to tell also the student that they are really aware what they are speaking about. Are they speaking about the quantum object itself? Are they speaking about measurement results of the quantum objects, or are they speaking about a model on the quantum object? That they really know on which level are they, how do they speak about the quantum object, the quantum states, and that especially the use of the model is very important for the student, that they really, for instance, don't say the electron or the quantum object is a particle, is a wave, but they really stick to that. We describe the measurement result with a wave model, for instance, that they really don't interfere the quantum object and the nature of the quantum object with the model we make of it, that they don't mingle the classical and the quantum world, but leave it separated.
Thank you. If there are no further questions, let us thank Jesche and also Chandralekha once again. Such a wonderful evening with two fantastic talks to celebrate the International Year of Quantum Science and Technology.
Yes, and I thank a lot for the invitation, and I'm happy to talk to you and to share my thoughts. Thank you.
Thank you. Thank you very much. So thank you, everyone. Thank you, Professor Chandralekha Singh. Thank you, Professor Geshe, for such wonderful sessions. So with this, we come to the end of this session, this day's program. Okay, so thank you and have a nice day and good night.
Good night.
Night.
Thank you, Mashood. Thank you, Mashood, for chairing the session.
Thank you.
I didn't say thanks to you.
Great organizing this. It was wonderful.
Yeah, it was really nice. The talks were really good. Thank you.
The full
Thank you,
session.
Mashood. Thank you, Alwar. Thank you, sir. Thank you, Rekha ma'am.